once we have a well-attended seminar. The speaker is Dr. Jim West. I wrote some of Dr. West's achievements, and then I decided not to write more than a page. So this is all the achievement that fit on the page. There are others, but I didn't want to take too long. He's a Bell Laboratory Fellow at Lucent Technology. He's a member of the National Inventors Hall of Fame. He's a member of the National Academy of Engineering. He's a fellow and past president of the Acoustical Society of America. He's a fellow of the IEEE. He has 47 US patents, 200 foreign patents, more than 100 papers, etc., etc., etc. And we're lucky to have him today speak about electret microphone that he invented. So it's going to be audio and visual.
That's for sure.
And I've been told it won't be more than 50 minutes.
I hope everybody stays awake over that time. What I'm going to do is basically give you some history on the electret microphone. As a matter of fact, I'm going to start out with condenser microphones because all of you may not be acousticians, and it may be just a good idea to start with the very basics. Then I'm going to move into some of the things that I'm doing now and a few sprinklings of what I am going to look forward to doing here at Johns Hopkins. If everything works, and it took me a long time to get that thing to go off, but hopefully it'll come back on within a few minutes. Here we go. And it's coming up. Condenser microphones have been around for quite some time, and it's a very desirable microphone, and it's a desirable microphone because both its frequency and phase response are constant over whatever range you intend to set it. You can set the resonance frequency above the expected range, and this can range anywhere from 10,000 hertz to a few 100,000 hertz. And you get a flat frequency response and phase response up to that point. But there are a number of problems with condenser microphones. First of all, it needs a bias of about 400 volts, 300 to 400 volts in order to be linear. The diaphragm, usually metal, is like a drum head. And when a sound pressure impinges on the diaphragm will move, okay? And because of the voltage and the small charge current that flows through here, across this resistor you get a change in voltage that's directly proportional to a change in capacitance. Now, condenser microphones with all of the linearity and so forth have one drawback, and that is they are very complicated from the mechanical standpoint, therefore very expensive. But most important, the need for the large DC bias. And now we're going to change subjects, and we're going to talk about material science for just a little bit, okay? On a molecular picture of polarization, starting out with a ceramic material, this material has a large dipole moment, but the dipoles are not aligned until you stress the material with heat, and a large DC voltage will align the dipoles. And now if you stress this material mechanically or electrically, you get an output. Polymers, namely polyvalidine fluoride, is also a polar material. The dipole moment is between the CFF bond, and again, it's a random process until you stress the material under heat and a large DC field. There were even devices made on this principle some years ago, earphones, but they had one major drawback, and that is the Curie temperature, and that's the temperature at which these devices depole, is around 80 degrees C. And black body radiation or just shelf life, usually these things will die, and so they don't last very long. We did something totally different. We took a nonpolar material, namely Teflon, FEP, and Teflon PTFE, and also stressed the material under a strong electrical field. You don't need temperature, but sometimes people use temperature. It's not really necessary. And we really don't know what happens. We think what happens is that the stress breaks the bond, creating a free radical and an ion. And now this ion is permanently trapped at where you break the bond. The important thing is that you have a constant, long-lasting electrical field charge that's stored in the material. And this charge is there until you reach the melt temperature of the material. It's just sort of locked in there, and you can't get rid of it. It's that lasting. And so what this allows is the ability to build a very, very simple transducer. A back electrode, an air cavity, a foil, and the back electrode has some perforations and also some ridges. And so now you don't need a torqued diaphragm. The diaphragm can just rest on the ridges of the backplate. And now the gaps in between the ridges is what allows the foil to move, and you get a voltage across the resistor that's again proportional to pressure. A little closer look at this. Here's the polymer material, usually about 25 microns thick, a metal layer on the top side, and the charge that's been placed inside the material here. Once you connect this across a large resistor, the charge redistributes and you get a field in the air gap. And now this field in the air gap replaces the need for the battery in standard condenser microphones, and things work very well. These microphones are even built as measuring microphones, and the last time I looked, there are something like 1 billion of these microphones are made each year. 98%, 95% of all microphones today are based on the principles that Sessler and I introduced. As a matter of fact, 40 years ago, last month, they released, there was a press release from Bell Labs that mentioned that.
Talking about those air channels or whatever, they should impose limits on top of frequency.
Of course.
What is it?
Well, it's the stiffness of the air cavity that provides the limits.
Yeah.
Okay.
So it's not 100 kilohertz.
You can make it anything you want. You see, I can close the air gap off, make the air layer very stiff, and now you get a few hundred kilohertz with the resonance frequency. You can make them various sizes, hearing aid microphones, and very popular in hearing aids and very large systems, and we made some about that big for very low frequencies because we need a large capacitance and therefore not quite as large a resistor to get the very large RC time constant. One interesting thing about hearing aids is that I was told by someone that before the Electret microphone, if you wore a hearing aid, you couldn't walk with the hearing aid on. And the reason for it is that the microphones that were used have basically a moving coil type device. And the vibration sensitivity of any transducer is directly proportional to the mass of the diaphragm. So here you just have a very thin layer, and now people can motor with their hearing aids on, which is a nice thing to know. Now remember, I said that the advantage here is that you get constant microphones. This means that you can stamp these things out and make millions of them, and their characteristics will be pretty much the same. Well, this opened up a whole new field, the possibility of using arrays of combinations of multiple microphones to form characteristics that are desired. And here we show two pressure microphones with a delay. If tau is equal to 0, you get a figure of 8, a first order gradient microphone. And the important number here is the directivity index, because what the directivity index says is that in an isotropic sound field, you get a 4.8 dB gain for a dipole over an omnidirectional microphone. So remember that, because you'll see this as we progress. The infamous cardioid microphone is what everybody makes and you can buy, and this is when tau is equal to d over c, where c is the speed of sound. But commercially, this is as far as you go. So you're stuck with a 4.8 dB directivity index from the standpoint of a commercial microphone. And I mean, this gain is good. Any gain in that environment is good, but we want to go further. We want to improve the directivity. And one way to do it is to make a hypercardioid where D over C is less than where tau is less than D over C. But we don't do things that way. This just shows you how things can be done. What happens is that I'm sorry for this, I looked for a better slide but couldn't find one. This is what we call a monolith. The microphone sits between two ports. There's a port here and a port here, and the microphone sits in between. And now, by the location of the diaphragm in this device, we can set D over C to anything we want. So we set that for hypercardioid, and we get an additional 2 dB gain. And in the top part of this, and I'm going to do this very quickly because it's important but not that important. If we look at close, at talking to the microphone close, and this is roughly 50 centimeters, in a quiet location, you see that you get about 1 sigma improvement of the circle indicates an omnidirectional microphone. But now if you go to a close and noisy environment, you see this almost jumps to 2 sigma. But what's really important is that if you go far away from the microphone, okay, in a noisy environment, the desirability of the directional microphone even improves. And this is because the really important thing is signal to noise. This is a picture of one of Avaya's, and Avaya, by the way, is a spin-off of Lucent, which was a spin-off of AT&T. So, you know, I'll oscillate back and forth between all 3 companies. But what I wanted to point out is that here's a monolith right here on this on the telephone, and this is very desirable in many situations for hands-free. Anybody sitting down this end is going to be okay, but people frequently try to use their telephones in conference situations, so somebody sitting back here is not going to be heard very well. So we continually look to find better ways of improving the directional characteristics of the microphone at the same time allowing everybody to be heard. Now, this microphone won't do it, but it's the beginning of a whole new trend in thinking about microphones. Not microphones per se as an individual element, but microphones combined with signal processing to do very special operations. Okay, and here's one. We have 2 pressure sensors with a little delay and some summers and adders. Don't worry about these equations. What I want to show is that the beta here, changing gain, will allow me now to put a 0 anywhere in the back plane on this microphone, just simply by changing the gain. Okay, and so this turns out to be a very simple device. And when you listen, you'll see that things work pretty good. If I've got the right one, let's see. Right. This is my colleague Gary Elko.
Microphone which selectively adjusts its directivity to minimize noise signals that arrive from the rear of the microphone. The system is composed of 2 omnidirectional microphone elements, which can be seen in the array that I'm holding: a forward element and a rear element. By combining the 2 elements in the signal processing algorithm, we can form the best directional pattern which fulfills specific constraints that require the microphone to be unidirectionally sensitive. As a final demonstration, I will talk from the front of the microphone with an interfering noise source in the rear. Initially, the pattern is set so the microphone is equally sensitive to front and back arriving signals. This is the interfering noise source, which we'll now turn on. It may be difficult to hear what I am saying since the noise source is so loud. To announce what's the adaptive microphone. I think you can hear a decided advantage of using an adaptive microphone in this situation. I can even rotate the microphone and still realize the same advantage.
And you see the important thing here is the fact that that the 0 follows things around close talking.
Okay, as you see.
Not ready for that yet, but thought I'd get it set up well. while I was there, okay.
That's a question. So
Mhm.
how does the microphone know which is noise and which is signal? I mean, there are two sources, right?
Oh, that's because the backplane contains the noise. You see, this is just, it won't do, you know, I sort of led you by the nose there a little bit. It won't do precisely what I indicated or to solve the problem, but you'll see later on that we're working towards solutions there. The backplane of the microphone, any noise that occurs in the backplane will be canceled, right? Now, this is a very nice laboratory device, and the demo that we showed you works very well. But multipath is a problem, okay? And anybody who understands acoustics will know that while this works very nice in a laboratory, when you put it in a real situation, it's going to work, but it's not going to be as clearly a differentiator as what I showed you a minute ago.
Did he rotate the backplane in that demo?
Yeah, he rotated the backplane, right.
And it continued to discriminate against the noise?
It continued to discriminate against the noise, but we played a little trick in that we had a nice soft cavity back there. You know, the walls were very absorbing, right? But if you're in a room like this, right, all bets are off on how well that will work.
And he did keep it in the back plane?
Yes.
He never turned
He
it
never-
so that it
right.
became the front?
Oh, he
Right.
didn't? Oh,
No,
okay.
no. Right. Now, of course, the next method of improving the directivity index is to go to second order, and this is just basically combining 4 pressure sensors spatially separated, as I've shown here. And now what you can get down to is a second order unidirectional microphone. And of course, this is the important number here, getting pretty close to a 9 dB directivity index. And so, you know, now we're sort of cooking. We're getting into the range where we can make a rather distinctive difference between using an omnidirectional microphone and something like this. But nobody wants to use 4 microphones. And so the way we accomplish this is by using 2 first-order differential microphones, okay? Now, you remember I had to change the D over C ratio, okay? And so that's taken care of by D2 here, the path around the baffle, so to speak. And just simply, if you look at this microphone, for a plane wave coming from the top or the bottom being differential, you get nothing anyway. But if you look at a plane wave coming from this direction, it arrives at this microphone, it's delayed, travels, and reaches this microphone, so you're going to get finite output. But now if you look from the other direction, wave coming from this direction, it comes into this microphone. Did I do that backwards? Let's see, from this direction, right, from this direction, the tau is such that these 2 sensors are just basically superimposed, okay? And you see that they're oppositely polarized, so you get 0 output. So there's 0 output from this direction, from that direction, and your main beam comes in from this direction. Now, this is kind of cool in that it works very well. One other thing, as I pointed out, one transducer is a mirror of the other. So actually you can achieve this with 1 sensor and an acoustic reflecting plane, because now you get the mirror image, which is precisely what you want. So 1 sensor separated some short distance from a reflecting plane will give you the same characteristics as the second order. And what do those characteristics look like? Here's some real data with the theory, the solid line, and going from 300 hertz to 3,000 hertz. Remember, this is telephone stuff, and that's what we're supposed to be interested in. So this is the range that we cover. There's some deviation in the back lobe, and that's due to slight amplitude differences in the microphone and some minor phase differences that can occur. Now, one of the interesting points is that noise-canceling microphones have been around for a long time, first-order noise-canceling microphones, and most of us know that they work pretty well. But what about second-order microphones? Using 2 first-order microphones separated by some distance d, the spatial sound field results in well, in a spherical sound wave with the microphone close to the mouth, and because these microphones are separated by some small distance, right, the curvature of the wave will give you a different output for the two senses, one close and one sort of separated. And what we can do is to, and this pressure difference is a function of where the microphone is from the mouth, right? Now, why are we concerned about this is the following. Second order goes with omega squared, right? So if you're real close to the lips, as you'll see, this thing sounds very well, but you get a little distance away and everything goes to pot. But again, using signal processing, we can create a simple lookup table, which is a function of the output of the two microphones depending on how far it is from the source. Okay? Everybody with me? Okay, and now everything works, and I chose the right thing. And this is me.
If I talk very close to this microphone, everything sounds all right. But now if I move it away from my lips, you'll notice that not only does
You see how fast it drops off?
the frequency characteristics are degraded tremendously. As I talk to it and move the microphone away from my mouth,
Yeah, this
you'll
is with
notice
the
that
adoption.
both the amplitude and the frequency characteristics remain reasonably constant over the distance. I can move it away and slightly down, and it does not change, or slightly up, and it does not change that drastically.
Okay, now, of course, there's a caveat here. The more distance you are from the microphone, what's going to happen? You're going to lose out on the directivity. Okay, just give me a moment.
I'm surprised all these demos have been working so far.
Yeah, me too.
But anyway, it is not related to what specific kind of microphone you're choosing, right? It's not related to electret microphone.
Well, it is in the following sense. If you're willing to pay $1,000 plus per unit, then it doesn't matter. But if you want to do this with, at $1 a piece, you have to use condenser microphones. And that's where the problem comes in.
Just because you need to use more than one microphone?
Yes. And these two microphones have to mirror each other, or have to have both frequency and phase characteristics are just alike. Now some interesting stuff. Lucent, when it wanted to become internationally known, decided that what they wanted to do was to advertise in Formula One racing. And rather than pay the $4 or $5 million that it takes to get your name on a car and on the sleeves of the drivers and so forth, Lucent offered technology in exchange. And so we sat down with people from Jordan, which is a team that we advertised on. This is, what are your problems? And they told us a very sad story. They said, well, if anybody follows Formula One, you know that Ferrari, Schumacher wins everything, and then comes BMW, and then Mercedes, and Jordan is way down the other end running a Honda engine. But these engines are really very interesting. 3 liters is maximum, normally aspirated, but they get horsepower up to 900 horsepower. These cars will run 300 kilometers per hour. Well, how do they get this very high horsepower? And that's by engine revs. And these engines rev up to 16,000 RPM. And anyone who can just make that translation knows that this is splattering noise throughout the audio frequency range. And the Formula One car sits just below the threshold of pain. I mean, the drivers have their ears plugged and so forth. And Jordan told us a very sad story. So one of the races that they were just about ready to win, the telemetering had shown that they were losing tire pressure in one of the tires. So the pit boss called signaled the driver and said, be careful, your right rear tire is losing pressure. But because there's not two-way communications, right, the driver heard fire and bailed. Okay, and so they lost the race, And so they said communications is really a hard problem. And, the only time the driver can talk back to the pit is when he backs off the engine to negotiate a curve. Right, well, you know, making a curve requires a lot of other concentration, so drivers don't talk very much. When we looked at what happened, we found a biscuit about an inch or so in diameter, moving coil microphone inside this helmet. And the drivers didn't like that thing in the mouth. The audio people would position it right at the mouth, and you just interesting to see the driver before he puts the helmet on, he puts his fingers up there and he mashes the noise canceling microphone right up against the inside of the helmet. And of course, what do you have? An omnidirectional microphone. Well, we went in with very small Electret microphones, and we certainly got improved noise cancellation. We got reduced vibration pickup, again, because reducing the mass of the diaphragm. Improved frequency characteristics, and last but not least, safety, because the driver didn't care if that little thing was up there. You know, it's about the size of an aspirin, and of course you can swallow that if things got dangerous, right? What I'm going to do next is play for you Heinz Herald running down the track and talking the whole time he's going down. And you'll be very lucky if you hear first and second gear, but he goes all the way up to sixth gear, running the engine out. I think I hope the guys in front are going to get blasted, but I can't do anything about that. Okay, you heard very little from the standpoint of the voice, right? But just by putting in a good microphone.
Right, now this is right in fifth gear. Now shifting up in sixth gear. Breaking into the parabolic.
Okay, when he says sixth gear, he's more than 300 kilometers per hour. And I mean, you know, flat out engine going down. Jordan said, Eureka, you know, this is worth the $3 or $4 million for advertising, and we became golden from the standpoint of the acoustics. But was I satisfied? No. So we decided that one thing that we wanted to do was see what we could do by planting another microphone in the car, just to pick up the engine noise and know none of the voice. And now to see what we can do in terms of processing it. And this is just a noise canceling scheme.
Right, now this is right in fifth gear. Now shifting up in sixth gear. Breaking into the parabolic.
Okay, another scheme.
Right, now this is right in fifth gear. Now shifting up in sixth gear. Breaking into.
Now, you notice a lot of vibrato in the voice. At first I thought that was the algorithm that was doing it. No, it's just the fact that we gotten the noise low enough so you hear him bouncing, and you hear the car really bouncing, and the vibrato in his voice. But, you know, this is still not good. And one of the reasons is that we located the microphone in the cockpit, and this is pretty far away from the driver. I have some new data that I haven't processed yet, and we put a microphone in the back of the helmet, which picks up none of the voice, but all of the engine noise. And so now we think we can probably do a lot better from the standpoint of that scheme. Okay, so we move on. Instead of now having two microphones, we have many microphones, and we build linear arrays. And I think for most of you, I don't want to spend too much time on this, but the point here is that if you have a linear array system, you can put delays in here to be able to change the angle for which the microphone picks up. In other words, you can steer it. Now, one thing that problem with linear arrays is that they're dispersive. And this means that the resolution of the array is a function of the length, okay? And so this means that when it's roughly as tall as I am, you may get a little directivity at 300 hertz, but now at 4,000 hertz, you're looking down a pencil beam. You almost have to look down the laser beam. So we played a trick that's used very often in loudspeakers, and then we built a harmonically nested array. Each of these little circles represents a first order differential microphone, okay? And so we have basically 4 arrays, 4 harmonically nested arrays. And the results here, and remember I talked about the image microphone, the fact that if I have a single first order, place it next to a reflecting plane, I get the cosine square. So here's the array placed against a reflecting plane. You get cosine square around this direction and about a 20 dB, 20 degree sensitivity in the direction of the antenna. Here's the characteristics from 500 to 800 hertz. There are a few side lobes here, all due to just minor differences in each of the microphones. Again, you can see that we can steer this over a wide range of angles. We get out to the far angles, we begin to have a little problem at low frequencies from the standpoint of steering. Disney had a display in Epcot City in which Alice has lost something, and they were using speech recognition to, you go in and you sit in this kiosk, and Alice is trying to find something, but you know where it is. So you tell Alice, look under the rock, or look to the left, or to the right, or whatever. And Disney used cardioid microphones in this thing, and they would, the person who's commanding it would reach and grab the microphone, look under the rock. And so sure enough, Alice would do that. But people who know and like microphones knew that that was about an $80 microphone and gone. And they were about ready to close the thing down. And they asked us this, well, is there anything that can be done about it? And sure enough, we put an array in the ceiling. And this thing worked as far as speech recognition is concerned, as well as a microphone right in the mouth. Okay, and it's the first application of these arrays, and also including speech recognition. Is that far enough? No. We go to two-dimensional arrays, 400 elements. Each of these circles represents a microphone. And again, you can see that there are 3 different densities of microphones, so we have a 3-octave array.
How big is that array? Small?
No, well,
okay.
Here it is here. This is a 400-seat auditorium. Sorry for this, but here's the array here. Now, for Bell Labs, Murray Hill is Mecca. That's where everything happens. And all the satellites, whenever there's a colloquium, it's always here and broadcast to satellite locations. And if Professor Meyer had said, look, this is being simulcast, please repeat the questions. I might remember the first question, but nobody remembers the second question. So what we did was we put this array in the ceiling, and we create 2 beams. Okay, one beam continually scans the audience looking for a talker, and as soon as someone talks, it steers the main beam toward them. And what does the beam look like? The same as the other, only in both directions. So this 20-degree beam will steer at the person, and if we look at the contour of the seating area, each one of these contours is 1 dB. You can see that everything is almost, is within 6 dB over the entire audience, and this hall will seat 400 people. It's kind of interesting to go in when people were assembling and we were tuning this thing to make sure it's working, and boy, we can hear some juicy stuff. Now, I want to go right to things that are happening today. And here we are working on a spherical array, a spherical microphone array. This sphere is about, has a radius of 3.75 centimeters. There are 24 pressure sensors that are located around the sphere, okay? And the way this works with the pressure microphones on a rigid square, it is a decomposition of the incident pressure into spherical harmonics. This is very similar to a standard eigen analysis. And this thing is rotationally symmetric along any axis through the center of the sphere. Well, I told you what that was. And we can get up to 3rd-order harmonic resolution, giving a maximum directional gain of 12 dB. Here, the red indicates highly positive from the standpoint of the sensitivity of the sphere. The blue, negative, and of course the bottom you can't see because this thing is slightly tilted. But here's the corresponding beam pattern you get for a spatial harmonic pattern in terms of sensitivity, as I've shown here. This thing is also steerable, as I said, through any axis through the thing, and this shows a third order. And so you see you get a very narrow beam. This is the maximum gain, about 12 dB that you can get for this, and of course you can steer it off in any direction. Now, why would we do something like this? Well, suppose you have one room. Could be a classroom, could be this room here, and you have a number of people who are talking, and somebody up here, like me, giving a lecture, and you put this microphone in the center. And it captures the whole sound field throughout the room, right? And so now all you need in an adjacent room or in a distant room somewhere is a decoder and a bunch of loudspeakers properly distributed. And now I can exactly recreate the sound, or the objective here is to exactly recreate the sound field that occurred in that room over here in a remote area. This could be very interesting from the standpoint of remote lectures. It could make things a lot more pleasant on the other end.
What do you have to send over that link from the first room to the second room?
Not very much. No.
Because there were experiments doing this with music over the internet, and they were sending just piles of data.
Yeah, but I'm talking about speech here only.
Oh, this is true.
It is also good for twice.
Could be. What I want to close with is some of the work that is currently going on at Avaya Research Lab, and some of this work I hope to import some of the projects down here. Teleconferencing is a very interesting phenomenon. Many of us have used it, and those of you who have know that it sucks. Okay, I think that's about the best thing that you can say about it right now. But there's a prediction that this can be a rather large business, somewhere around $10 billion in 06. Recently, there was a commercial where somebody was trying to reach somebody on a conference call, dialed in the number, and got the audex. He says, "Oh, gee, where is Tom?" And pretty soon the door opened, and Tom walked in, and they says, "Oh, we're flying again." It was an ad from airlines. Well, people may want to travel, but I tell you, if it's possible to get your work done without spending a day in an airport and on an airplane, that might be very well worth it. Now, as I pointed out, existing technology has many drawbacks. But one of the things that we're looking at, that the new technologies that are emerging, one, to go to wideband, and this is from 50 hertz to 77,000 hertz, which is normal telephone bandwidth is 300 to 3 kilohertz, and looking at building full duplex speakerphones and even going to stereo. And in fact, I have a full stereo echo canceller that operates on this laptop, and it doesn't choke it. I mean, you can still do a few things with that running, but it doesn't stop running. It gets a little slow. And then, of course, the wideband comes from the internet protocol. Coders are very important here because you want to get the bandwidth, especially if you're talking about stereo. Even in the IP network, you still want to conserve bandwidth if you possibly can. And what I'm going to do here is show you a number of coders that already exist. The first one's 2.4 kilohertz.
The approval was worn in a thin silver ring.
Now this is over telephone bandwidth, that what you're hearing there. We double it or go to 8.
Strongly and with firm strokes. The approval was worn in a thin silver ring.
Some improvement, but still basically telephone bandwidth. 16 kilohertz.
Sunday is the best part of the week. The doctor cured him with these pills.
Now for the big quantum leap, going from telephone bandwidth to wideband, 16 kilohertz.
Sunday is the best part of the week. The doctor cured him with these pills.
Okay, so Actually, we need not go any further. 16 kilobits might just be good enough, but
Kick off the
32
new
kilobits.
year with a gift from 800 Flowers. Just visit any 800 Flowers store during January's Winter White Sale, and you'll enjoy special savings on white.
Now let's go to FM quality.
Kick off the new year with a gift from 800 Flowers. Just visit any 800 Flowers store during January's Winter White Sale, and you'll enjoy special savings on white.
Well, I'm sure you can hear the difference. And if we can get telecommunications with that kind of quality alone is going to help tremendously. But now if we look at echo cancellation, and starting out with a single echo cancel, you have a talker here, and it's picked up by this microphone, broadcast over this loudspeaker, and it can come right around and go back. And because we have a gain greater than 1, this means that the system will be in oscillation, right? So what we do is put an echo canceller here that mimics this path and looks at what comes in this direction, and whatever is down here from that looks like this will be canceled by the echo canceller. So you don't get singing, and if it's truly full duplex, meaning that no gain is switched, this makes it easy to interrupt, and you can have a two-way conversation that is pretty normal. But now if we introduce stereo, there's a big problem. And that is that both of these signals are coherent, so both microphones can pick up the same signal. Mind you, this is only half the picture, right? This is duplicated for the other room. But the problem is, how do you separate? How do you know H-hat1 from H-hat2? Well, Jacob Benesti came up with a real interesting solution. What he did was to introduce nonlinear distortion in both channels, different nonlinear distortion in both channels. And now these channels are marked, so now the echo cancelers can separate them. And you can have truly stereo, full duplex speakerphone. And so you say, okay, why stereo? What's so important about that? Well, I have a demo here, and what you'll hear is three people talking, okay, over a mono channel, and then we'll break out into stereo. And what this does is that it's what we call a cocktail party effect. If you're in an extremely noisy environment, mainly because those of you who have good hearing in both ears, you can pick up one conversation over the other. And you do that because you have two ears, right? And this is the reason that we want stereo, because if we can bring stereo signals to you, this means that the ability to resolve may indeed be there. And if I've done things correctly, and probably the only people that are going to really get that are the people who are sitting right in the middle of these two loudspeakers. Apologize for that, but there's very little that I can do. You'll hear first mono, and you'll find that it's hard to discriminate one from the other. And I know what I can say.
Verizon Wireless, the nation's largest wireless carrier, with Lucent Technologies today announced a 3-year, $5 billion contract which positions Lucent to become the largest supplier of Verizon wireless lead generation and mobile networks.
See a lot of lips moving, but it's hard to make anything
Verizon
out.
Wireless will begin to deploy its first phase of 5G technology.
Yeah, that's your host.
CCA 2000.
Kathy Shipley, too.
Later this year. This introduction will be
Now stereo.
Real-time communication. Surf Talk will enable you to reach
products, services, and software. Verizon Wireless will rapidly introduce
We are excited to be
the
working with
services substantial additional
to get to soft innovation brings us closer to our goal.
Third-generation networks
Vice
require
President,
high-speed
VT
data
United
networking
Internet
systems
Services.
to
In
support
Europe,
mobile internet
Telecom
sessions.
Global
As
Network
world
will
leaders in
extend
voice
from
over IP,
Germany to
we are
Austria,
replacing
Netherlands,
VT
UK, France, Italy, Switzerland, Belgium,
Back to mono.
Requiring very high-speed data transmission. Some of these applications operating over Verizon Wireless spectrum are being shown in both live drive demonstrations as well as announcements at the CES.
Stereo.
A-Star ADM 16 to
This
1.
agreement reaffirms the long-term relationship.
But we have found the visual channel absolutely essential.
Oh, yes.
That even in the mono, I could distinguish the 3 channels in the mono, and I found that, and I just discovered that's why I can't conduct a conversation with somebody in the room and somebody on the phone at the same time. If I had your speakerphone, I could probably do
You
that.
could probably do that, right,
So
because you could separate
that's
it.
an amazing, yeah.
Yep. The end. Questions?
When you were talking about introducing the distortion so you can figure out the two transfer
Mm-hmm.
functions, is that distortion that's always added, or is it just for some calibration phase to figure out what those transfer functions are?
No, you have to have that distortion throughout. The distortion is rather high, around 10%. But you can't, he set this so that it's inaudible for speech, but it just rips music apart. Yeah, it has to be there all the time.
Okay.
This in the scheme, yes.
Returning back to those ions, is it still the same situation? Nobody knows precise mechanism?
From the standpoint of the charge storage, the interesting thing about how this charge is stored, we still don't understand a model, and we very much need a model. And the reason is that Teflon, back electrode microphones, this is where they melt the Teflon on the back on the back plate, and then they're free to use the material with any mechanical properties that they want.
What is the concentration of those ions, or that's called impurities like that?
Could be impure. Well, there are theories that range from impurity trapping to the one that I showed, to breaking the bonds of the material.
What is the concentration? At least you can say things.
Of charge, we can go right to the breakdown strength of the material, which is 10 to the minus 7, minus 6 coulombs per square centimeter. So we can get very high charge with that in the material.
Can you translate it to how many particles per centimeter?
No, I'm sorry, I can't. I don't know how to do that.
Has anybody looked at them from, say, a spectroscopic point of view, looking at the spectra?
No, we built what we call a laser, a LIP method, a laser-induced pressure pulse, where we can resolve the placement of the charge to within a micron in the material, but we can't get any better than that. This is an area that deeply needs new thought, and people who can approach this from a different perspective, and something I'd very much like to talk with you about in the future. I think we talked a little bit about that when I was here before. Yes?
Could you speculate on the impact that MEMS microphones will have on microphone technology?
Oh, you want me to continue? I have some of that. Yeah, the interesting thing about MEMS microphones, I do have some, we have done some work there. But this is a long time ago. As a matter of fact, Professor Bush-Vishniak was there when, at that time, working with us, and I made a back-of-the-envelope calculation that says this will never work. And the reason that I said it would never work is with a very simple calculation. I found that the limit is noise, okay? And the smaller you make the capacitor, right, now the more problem you have as far as noise is concerned. Not only that, very small diaphragm, very high stiffness, okay? And so this combination sort of says that this is a problem that's sort of negative in the sense that the cost of silicon per square centimeter is fixed, right? Now, so the only way to make these things work is to go from micro to macro to make them larger, right? But the thing that catches you there is that you can buy electret microphones with FETs. If you want to buy a couple of thousand of them, you can buy them for less than 20 cents. So I think I'm going to be in business a long time with the electret microphone before anybody finds a better way. I mean, I'm still looking. I hope that there are better ways of doing things because of the drawbacks here that still exist with the electret. But and that's not to discourage you if you're interested in MEMS, because there are a lot of ways of improving. I better not do that. I do have some of the latest work that we're doing, and that we're increasing the area by making a sort of a tent-like structure in silicon and having the stresses and the hinges in the right place. This thing comes up and forms a device like this, and And now you can increase the area, which is moving in the right direction, but not all the way. Yes?
You know, when you just started talking about first order, second order, my thought immediately was, why wouldn't you use arrays? So, but then you talked about arrays, and all this is sort of repeating to me. Radio astronomy and the radar technologies, you know, optics, interference, gratings, diffraction gratings. But if you go back to the same things, they use, for example, in optics, instead of arrays, they can use mirrors. Anyway, you was talking about flat mirrors. And if you are willing to use any mirror, why not use a parabolic mirror? And then we're coming back to the 1940s when people used to, discover those flights, the bombers. They use essentially a sonic radar, a big parabolic mirror with one listener, huge, directionality was huge.
There's one big problem between light and sound.
But they use sound. It was sound.
I know, but when you mention curved dishes and so forth, right? The problem is that with light, you can do this analysis based solely on intensity. But in sound, you can't do that. You have to take the phase into consideration, right? And so now you have a parabolic dish, right? And that's going to have certain cutoffs, and it's going to have certain, you're going to take on the characteristics of the shape of that dish. And it's not going to always be broadband, right?
Of course, but the problems are exactly the same.
They are the same,
talking about
right?
Waves, forget about everything else.
Yep.
It must be. If they're phase sensitive, they must be the same phase sensitive.
Yes.
In radio domain, in optical domain, or in acoustics, it's the same thing.
You're right. You're right. Other questions? Yes.
I was curious. Most of what you've talked about has a fairly small bandwidth, and you're talking mostly because you're phone. Is there a problem with Electrek when going to?
Not at all.
Okay.
In fact, even the arrays, you see the sensitivity or the frequency range of the array is primarily controlled by the spacing between the elements. And so our spacing is nowhere as small as you can possibly get. We can use smaller transducers, and even on this array you can get closer. The hope is that using the same technology and same size transducers, by closing the distance down, we'll be able to get to 7 kilohertz with no problem at all.
Any more questions? Well, I'd like to thank the speaker again.
Well, thank you.